Hey, this is Jacob Levins, and welcome to my personal Solidworks project, the 6-cylinder 4-stroke engine. All thermodynamic analysis will be done with the reversible Otto cycle. The primary purpose of this project was to learn more about the Solidworks program and how to create complex systems and to analyze them with thermodynamic analysis. By stating that any SolidWorks part or component utilizes standard CAD operations, this can be interpreted as I only use the basic SolidWorks operations such as sketches, lofts, extrusions, etc. for that part. The main body of the engine is the engine block, which houses the cylinder assemblies. Standard CAD operations were utilized for this part, as well as the rib function, which adds a thin wall support along a sketch. The cylinder assemblies are the core of the 4-stroke cycle that causes the combustion to occur by increasing and decreasing properties such as pressure, volume, temperature, and entropy. The cylinder assemblies utilize standard CAD operations and demonstrate the importance of using multiple axes in SolidWorks. The cylinders work together with the rocker arms and valves to complete the 4-stroke cycle. The rocker arms and valves allow fuel into the cylinder chamber and let exhaust out of the cylinder chamber at a different step of the cycle. The rocker arm assembly utilizes the helix and spiral function to create a spring. All other parts created in SolidWorks are used with standard CAD operations. The cylinders and the rocker arms are timed perfectly to allow the cycle to operate properly. This timing is done via belt wheels and a belt that turns the camshaft connected to the pistons and the crankshaft connected to the rocker arms in the proper time. The belt wheels utilize gear and gear ratio operations in both the assembly and in the individual parts, while the crankshaft and the camshaft utilize advanced linear patterning and mirroring techniques in SolidWorks. The first stroke of the 4-stroke process is the intake stroke. The piston moves down into its chamber while fuel enters the chamber through the intake valve. This is an isobaric process. The second stroke of the 4-stroke cycle is the compression stroke. The piston moves up in its cylinder, decreasing the volume and increasing the pressure. This compresses the gas that was previously pulled into the chamber. This process can be estimated as both adiabatic and isentropic as estimated by the reversible Otto cycle. The gas is then ignited with a spark plug and the pressure quickly jumps very high. This causes the third stroke of the 4-stroke process, the power stroke. The piston moves down into its chamber as the volume increases and the pressure decreases. This process can be estimated as both adiabatic and isentropic as estimated by the reversible Otto cycle. The fourth stroke of the 4-stroke cycle is the exhaust stroke, where the piston moves up, decreasing the volume, while isobaric, causing the exhaust to leave the chamber through the exhaust valve. The turbo housing is used to increase the power output of the engine by supplying compressed air to the engine intake manifold, so increased fuel may be utilized for combustion. The filter is used to filter the air. The hoses are used to transfer the gas from one point to another on the engine. The intake manifold utilizes unique mirroring, shelling, and extrusion techniques, while the hose utilizes 3D sketching. The filter utilizes standard SolidWorks CAD operations, while the turbo housing utilizes SolidWorks surfacing. As well, we have the oil pan at the bottom of the engine to catch any oil that may drip from the engine. The exhaust manifolds on the sides of the engine are used to release the exhaust created during the cycle. And there are many engine covers surrounding the engine in order to protect it from the outside elements. Thank you for watching. This has been my analysis of a 6-cylinder 4-stroke engine in SolidWorks.